Okay. So yesterday we talked about the chain rule. The chain rule talks about function composition. Today we're going to be talking about implicit differentiation, which, as you'll see, is a continuation of the chain rule. So if we wanted to, review some, like the big ideas, like if I were taking the derivative with respect to x of x squared, we know from last week that that answer is what? 2x. The chain rule says if I want to take the derivative of something squared, that something maybe being a function of x, then it starts off 2 times that thing, but then we have to multiply by the what? Oops. Not the y, but the derivative of that thing. You follow? If we want to take the derivative of sine of x, from last week we know that's what? Cosine of x. But if we want to take the derivative of sine of something, it's what? Cosine of that thing times the derivative, right? So, when the letters match, we're just essentially multiplying by 1, because the derivative of x with respect to x is 1. If we've got something else and the letters don't match, then chain rule says we have to kick out that derivative. Is everyone cool with that? This is pretty much what we're doing today. All right? It's more chain rule, but chain rule that looks kind of like this. All right, so let's take a look at this curve. I've got it fired up in Desmos here. So this curve is the graph of this equation. All right. It's not convenient to solve y as a function of x or x as a function of y. And in fact, even if you did that, if you look at this graph, you can tell that y is not a function of x globally because the graph fails what test? Yeah, vertical line test. There it is. There's a vertical line. Hits the graph 3 times. That means for x equals -4, there are 3 different y values for it. You follow? And to be a function, every x gets matched with only one what? Y. So this graph, they say, fails the vertical line test. So in other words, globally, y is not a function of x. And if I turn my head sideways, I can check the what? Horizontal line test. The graph fails that as well, so that tells me that x is not a function of y either. You follow? The problem is when we've done derivatives, if you look at our definition of derivative, it's in terms of a function. You follow? And so how do we handle that? So even though globally y is not a function of x, if you think about differentiability, differentiability is the same as local linearity. So when we talk about differentiability, we don't care about what's happening everywhere. We're just happening as we zoom in on a point. So like if we pick the point here 4, -1 and zoom in on it, not only locally does it look like a line, it also means that locally it's a function. You follow or not? Okay. But if we tried to find out what that function was explicitly, it'd be a challenge to solve. Oops, let's do this in blue. It would be a challenge, to say the least, to try to solve y as a function of x that have enough restrictions to narrow the formula down so that it works just near the point x equals -4. You follow? So the good news is we can use the chain rule to help us find the slope of that line at when x is -4 and y is 1 without having to actually solve for y. Okay, so that's where the chain rule gets involved here. And that's the concept of implicit differentiation. So when you have y equals f of x, this is often called an explicit formula. y is a function of x explicitly, because you basically got y solved completely in terms of x. In the example we're looking at here, x squared plus 2xy plus y cubed equals 9. We can think of this as defining y is locally a function of x, and this is defined implicitly because we haven't solved explicitly y is a function of x. All right? So that's where the word implicit comes from in implicit differentiation. So implicit differentiation is a way to get the derivative without having to solve for the dependent variable. We're going to start with an equation involving both letters, and we'll be able to find the rate of change of one with respect to the other without having to explicitly solve for one as a function of the other. Okay? That's the whole idea. That's why it's called implicit differentiation. So, once again, just going back to what we did, seems like forever ago, but it was just like a week ago, right? If you think about it. When did we do section 3.1? Last Tuesday. Slope of the tangent line, that's the derivative. And we've got the dy dx. And the point we're interested in here is the point -4, 1. So what you're going to notice in this section is that when we talk about the slope of the tangent line, we need to include not only the x value, but also the what? The y value. Because if I look at my graph, right, if I look globally at the graph, if I look at x equals -4, it hits 3 different places, and each of those places you're going to have a different slope. You follow? So whatever formula we come up with for dy dx, it should not only depend upon x, but also the what? It should also depend on the y. So that's what we're going to find out. So here's what we do. I'm going to start off with the formula here. X squared plus 2xy plus y cubed equals 9. And we're going to think that locally y is a function of x. And we're going to take the derivative of both sides of this equation, thinking of y as a function of x. Or thinking of y like something like this. You follow? So anytime we take a derivative with respect to x, we're going to have to use the chain rule. All right, so we're going to take the derivative of both sides with respect to x. So we go back to last week and start using the properties of the derivative. If you plugged in an x and a y to the left-hand side, you'd figure out the x squared, you'd figure out the xy, you'd multiply it by 2, you'd figure out the y cubed, and the last thing you would do with those 3 numbers is what? Add them up. So the first derivative property we're going to apply is the sum rule. So it's the derivative of x squared plus the derivative of 2xy plus the derivative of y cubed. And what's the derivative of a constant? 0. So far, so good. Now, what about the first term? I'm taking the derivative of x squared with respect to x. So we know from last week that's just going to be what? 2x. Plus, what rule can I apply here? I'd plug in the x, I'd plug in the y, I'd then multiply by what? 2. So I'm multiplying by a constant. And so if I multiply by 2, what can I do with the 2? Bring it out. That's your constant multiple rule there. And now let's take a look at the last term. I'm taking the derivative of y cubed with respect to x. Now that's not x cubed, that's y cubed, and we're pretending that y is a what? Function of x. So what rule do I have to use here to take that derivative? I'm not taking the derivative of x cubed, I'm taking the derivative of something cubed. And what's the derivative of something cubed? 3 times that something squared times its what? Times its derivative. So do you see why we're using the chain rule there for that term? And we could use it here. The derivative of x squared is 2x times the derivative of x with respect to x, but the derivative of x with respect to x is 1. Do you see what's happening here or not, folks? Are we good? That's your chain rule. Okay. So now I got this. What rule do I have to use then for this term? I've got xy, but that means that x and y are being what? What's the operation in there? Multiplied, right? So if they're multiplied, I have to use what rule? Product rule. You with me or not, folks? Okay, so I've got the 2. I'm going to go ahead and put parentheses here because I got to multiply by the whole thing. I got to hit this with the product rule. The product rule says I take the derivative of the first factor times the second plus the first times the derivative of the second So I got my 2x plus 2 times, and what's the derivative of x with respect to x? 1 times y plus x times, what's the derivative of y with respect to x? I don't know what y is, but we're going to call that what? Y prime. Okay. Does everyone see where the y primes are coming from and why they're showing up? So I'll write this again on the next slide here. We've got 2x plus 2y plus 2xy prime plus 3y squared y prime all equal to 0. Now, what I'm looking for, the slope of the tangent line, that's dy dx, that's y prime. So now I need to solve this equation for y prime. Now, what's nice about the chain rule is anytime you use the chain rule, that y prime is going to pop out as a multiple. So whatever the heck is going on, the y prime is always going to be a multiple, which means you'll always be able to get everything without a y prime on one side, factor the y prime out, and then divide by the coefficient of y prime. Right? So every single time you're going to be able to do the following. Subtract everything over that doesn't have a y prime in it. I'm going to subtract over the 2x, subtract over the 2y. And then we'll be able to factor out the y prime. Once again, every single time, because that's how the chain rule works. And then we'll be able to divide by the coefficient of the y prime. So this is how your implicit differentiation is going to work every single time. You're going to have an equation. You're going to take the derivative of both sides with respect to whatever, in this case x. you'll go through any letter that's not an X, you're going to apply the chain rule to. Every time the chain rule gets applied, it's going to pop out as a multiple. So now you're at the algebra part. Since the y prime always pops out as a multiple, you'll always be able to subtract off everything without the y prime in it to the other side. You'll be able to factor out the y prime from the terms that have it in there, and then you'll be able to divide by that coefficient. Right? This will happen every single time. So those are your steps to solve it, and there you go. There's your y prime. Any questions on the algebra there? You see what's happening? So for us, the point that we care about is negative 4, is it negative 4, 1? So the slope of the tangent line is the derivative dy dx at negative 4, 1. So we got negative 2x minus 2y. I should be specific here, since there's lots of letters running around. Xy is negative 4, 1. So that would be negative 2x minus 2y all over 2x plus 3y squared evaluated at the point negative 4, 1. So that means everywhere I see an x, I'm going to substitute in a what? Negative 4. Everywhere I see a y, I'm going to substitute in a 1. And let's see what this slope works out to be. In the numerator, what do I get? Be careful, not negative 10. But yeah, because this gives us a what? Yes, that would be a 6, and then the denominator get a what? Negative 5. So negative 6/5 for that slope. And now I can just plug into my tangent line. So tangent line is y equals the slope of the tangent line, x minus x naught plus y naught. So I got a negative 6/5, x minus the negative 4 plus the 1. Negative 6/5, x plus 4 plus 1. And what's going to be the ultimate check that that really and truly is the tangent line? What should happen when I graph that line? It should look the same as the curve when I zoom in. You follow? Any questions on plugging that into the line for me? All right, let's look and see. And look at that. So look what happens. As I zoom in near the point negative 4, 1, can you tell the difference between the line and the curve? So that's your local linearity. Make sense or not, folks? But you notice here your derivative depends upon both x and y. So depending on the x and depending on the y, the slope will change, as we've seen it should. Okay? So that's kind of the new thing with the implicit differentiation, is your slope is now a function of both x and y. All right, example 2 is a video. So here's the derivative. Basically, you're going to rework this problem. This is on the same curve, except we're looking near the point 3, 0 instead of the point negative 4, 1. All right. So you plug it in, and you get your tangent line. And then you check it. All right, let's take a look at the unit circle. That's your good old unit circle there. Once again, does this equation describe y as a function of x? Well, no. It fails the vertical line test. Does it describe x as a function of y? No, fails the horizontal line test. You follow? So. However, locally, if I pick any point on this graph, locally, well, except these points here, we'll talk about that in a minute. But if I pick, any of these other points, we should be fine. So let's go ahead and find an expression for y prime, aka dy dx. All right, so the way we do this is start off with your equation. You take the derivative of both sides with respect to x. On the left-hand side, you've got x squared plus y squared. So the first rule you can apply is the what? Sum rule. What's the derivative of a constant? 0. Now, what's the derivative of x squared with respect to x? You got the same letter here as here, so that's just going to be what? 2x plus. Now, I'm taking the derivative of y squared with respect to x. So it's not x, it's something else. So what's the derivative of something squared? 2 times that something times the what? Derivative of that something. So that's the one we need to chain rule on. You see why we don't need to chain rule in the first term, but we need it on the second term. Now, as promised, the chain rule popped out as a multiple, so I can now subtract over everything without the y prime in it. So I'm going to subtract what from both sides? The 2x. And now I can divide through by the coefficient of y prime. So I'm dividing through by what? 2y. And I'm dividing here by a variable, so this goes back to what we mentioned before. Y can't be what here? 0. So we'll see that here in a minute. There it is. So let's take a minute and look at some of the consequences of this formula. So we've got dy dx is minus y over x. Let's go over here on the old unit circle. And we'll put coordinates here. Okay. I'm sorry, it's minus x over y. I got it backwards. I was thinking ahead here. Okay. Now, do you see why we have to exclude 0? Or y equals 0 here? Because algebraically, what's happening there? Algebraically, it's a 0 in the denominator. But let's look at the 2 points on the unit circle where y is 0. That's these 2 points here. You follow? Let's see what happens when we zoom in on those. We're on the unit circle, so let's go like -2 to 2, -2 to 2. And we'll square it up. There we go. Okay. So let's look at 1, 0. Let's start zooming in on that. And you tell me what happens and why the derivative dy dx doesn't exist there. Does it look locally linear? The problem is it looks like what kind of line? Vertical line. So we have a vertical tangent there. You with me or not, folks? So vertical tangent, you've got infinite slope So dy dx doesn't exist on that. So that explains that. But something else I want to point out is let's look at this line. Let's look at the radial line. So that's the line that goes from the origin through the point. And what would be the slope of this line? So how far over do I go? How far up do I go? Well, how far over I go, that's your x. You follow? And how far up I go is my what? Y. So the slope of that line would be y over x. You with me or not? Okay. The slope of the tangent line is minus x over y. What's the relationship between those two fractions? They're negative reciprocals of each other, right? Now, what do you know about slopes? If you have two slopes, m1 and m2, and they're negative reciprocals of each other, what does that tell you about the two lines? Does that ring a bell? Means they're perpendicular, you follow? So this is another way to see that the tangent to the circle is perpendicular to the, bless you, to the radius of the circle at each point. That's a little fact from geometry. Okay, so you can kind of see that here in this formula. Here's another note. You notice x and y completely symmetric. You follow? What do I mean by that? If I switch the x and the y, I'd end up with the exact same equation. You follow? Now, when we took the derivative, we were taking the derivative with respect to x, but that's kind of like just how we've always done it. We've always had y depend upon x. There's no reason that we couldn't have x depend upon y. You follow? So let's see what happens if I take the derivative of both sides with respect to y. It's a derivative, so the sum rule still applies. The derivative of a constant is still what? But now, since we're thinking of x as a function of y, what's the derivative of x squared with respect to y? What would this be? So what rule would I have to use there? Chain rule. So it'd be 2x times x prime, where x prime here would be what? You with me or not, folks? What about the derivative of y squared with respect to y? That's just going to be what? Just 2y. I don't need chain rule there because it's the same variable. You follow? And now I could solve this for x prime. I could subtract 2y off, divide by the 2x, provided x isn't 0, and I would get x prime or dx dy to be minus y over x. So what would be the bad points here? If x is 0, well, first off, notice here, dy dx would be like a minus 1 over 0, which is undefined. But what's dx dy here? It's 0. So if I just turn my head and I look at the xy slope, it's 0. You with me or not? Because, why is it 0? Because that's the rate of change of x with respect to y. And at that point, the x isn't changing, is it? The y is, but the x isn't. You with me or not? That's what makes it a vertical line. Okay? But of course, these are now a problem. because the x is changing but the y is not. You follow? So the dx dy here, that's not going to exist because the x is changing but the y is not. Okay? So that's something you can do with implicit differentiation that we couldn't really do before. We didn't really care to think about. But we can switch up who's the dependent variable, who's the independent variable. You follow? And there's an exploration at the end of the section that talks about that a little further. So I encourage you to work through that. Okay. So let's go back into the land of y as a function of x. And we have this. For our dy dx. What if we wanted to get the second derivative? Okay. Why would we want the second derivative? Well, we've seen that second derivatives, I mean, they talk about the rate of change of the rate of change. They talk about how the slopes are changing. There's accelerations and things like that. So what if I wanted to get the second derivative? So just a little reminder here of some different ways to denote the second derivative. You could have y double prime. You could have d squared y dx squared, dx squared. These are all ways to denote the second derivative. Right? So the way you get the second derivative is you take the derivative of the what? First derivative. So that's what we're going to do. So I'm just going to recopy this on the next slide so we have enough room to work here. Okay. So once again, all the derivative properties are going to work here. So if you plug numbers into this, you plug in your x, you plug in your y, you divide them, and then you take the what? That negative, which is really a negative what? 1. What can I do with that negative 1? Yeah, we can factor it out front. All right. Now, we're back to thinking of y as a function of x. So what rule can I use here? I've got x divided by y. So what rule could I use? Quotient rule. All right, so here we go. Quotient rule. So I got that negative out front. I got the low function and the high function. So low d high would be y times the derivative with respect to x of x minus high d low, x times the derivative with respect to x of y, and then we square the bottom and off we go. I got the minus out front. Denominator is y squared. I've got y times, what's the derivative of x with respect to x? Those are the same, so that's just going to be what? 1 minus x times, what's the derivative of y with respect to x? That's what we call what? Oops, y prime. Everybody good up to here? Right? Now, what we'd like to do is get everything in terms of just x's and y's. So I'm going to go back and look at what we had for y prime. I had y prime was minus x over y, so I'm going to substitute that in there. You follow? So we'll do that. So I got that minus out front. I got that y squared down there. I got y times 1, which is y, minus x times y prime, but y prime is minus x over y. Everybody good up to there? Now I want to simplify this. So I got my minus. I got a y. Here I've got a minus. So what do I get out of this? This is a minus x over 1. So minus x times minus x is what? Plus x squared over y cubed. Excuse me, y squared. I'm getting ahead of myself. And how am I going to get rid of this complex fraction? I'd have to multiply numerator and denominator by y. So once again, here's some algebra coming in. What's y times y? Y squared. What happens when you multiply the y to the second term here? Cancels out. And now y times y squared is y cubed. And so you may be perfectly happy with this answer, x squared plus y squared over y cubed. And then, of course, you'd go off to check the back of the book. And the back of the book has this answer. So the back of the book, either you did something really wrong or there's something that you're missing. You follow? And once again, this is one of those things. Implicit differentiation, hard to check on Desmos because it's hard because you can't graph it. You follow? So what's going on here? Well, remember the original equation we started with was what? So you see what happened? That x squared plus y squared popped up, and that got replaced with what? 1. You with me or not, folks? So if you've been working through the homework and the examples on the handouts and seeing those trig equations, those trig identities pop up, it's the same kind of thing, except now we're using the equations that describe the curve itself as identities. And there's some amazing things that can happen as you work through the homework there. Okay, example 4, great example to work through. Find an expression for dy dx. That's pretty complicated. The curve looks pretty groovy. Let's take a look at that curve. We're looking at the point. We're looking at the origin. It's a nice little safe point. So once again, locally, looks like a line. You follow? Totally differentiable. But let's zoom out and check this out. All right? There's all kinds of craziness going on. Shouldn't be too surprising because you've got y inside the sine. And we know that sine repeats itself like every 2 pi units. So there's periodic stuff going on there. Yeah. And I encourage you, once again, during the regular semester when we have more time, there's a project I give the students, and one of the projects students have done in the past is they explore some of these implicitly defined curves. Because you'll look in the homework, and some of these curves will have names. All right, like the Witch of Agnesi. It's called the Witch. Why is it called that? Right, and then here's an interesting curve. Anyhow, locally it's linear, so we're going to find the derivative of that. So we can work through that. Example 5, another example. This is a lot like the one we did together today. This one's got some trig in it, so it's up to you. You may want to do example 5 first. Doesn't matter. You're looking at the tangent line there at -2, 4. Then there's a challenge here if you want to dive in and work through that challenge. And then we have an exploration. So you take the example we did here in example 5, And instead of thinking of y as a function of x, you think of x as a function of y and take the derivative implicitly with respect to y, and then compare dy dx and dx dy, and see what happens. Because there's a general phenomenon that happens there, and if you think a little bit, you'll see why it happens that way. Okay, it turns out they're just the reciprocals of each other, which hopefully makes sense because you're looking at a ratio of delta y over delta x versus a ratio of delta x over what? Delta y. So in the calculus, that comes over as well. Okay? You got a bunch of homework.